So in the last video, we introduced the concept of solving a system of two linear equations, looking for what's common to both, by graphing two lines and looking for where they cross. Now what we want to do is talk about some vocabulary that is associated with solving systems. So we have three different situations that can happen. So the first thing I want you to notice is in the first situation, this is what we saw last time in our opening examples. And that is that the two lines crossed at exactly 1 point. So in that situation, there is exactly one solution. There is exactly one solution. So what we say in this situation is that the equations themselves are independent. So when we talk about independent equations, that's going to mean, or how I would encourage you to think of it, if I can spell, that they're different. So independent equations, I just want you to think to yourself as we're graphing these lines, that the lines are different. So I often say, maybe think about a couple, and as long as they're different, then they're kind of independent of each other, right? Two people, maybe they're dating, they're a couple, but as long as they're different, they're independent of each other. Okay, so I'll elaborate more on that later. Okay, the other piece of vocabulary that we want to think about is that the system, we describe the system as being consistent. So this would be an example of a system that is consistent as long as there is at least one solution. And of course, that's exactly what we have here. All right, so let's take a look at our next situation here. So in this next situation, we have no points that are satisfying this system. These lines are parallel, so no points have satisfied the system because they never cross. They have nothing in common. So in that situation, there are zero solutions to the system. Now, I would still say, though, that our equations, if we were to describe those equations are still described as being independent because, once again, the lines are different. Okay? They're not the same line. They're independent of each other. Okay? They're different. However, there's no longer at least one solution. There is no solution. So when there is no solution, this is when we say a system is inconsistent. So inconsistent vocabulary with systems means there is no solution to that system. Okay, that's key. That's key. All right, the last situation, and you notice it's kind of said there, it says they are the same line. It's written out here. How that is often shown in a situation like this is they will often put a double arrow on the end of a line indicating that one line is sitting right on top of the other line. So that's another way to express that you have essentially two lines that maybe at first they kind of look like they were in different forms or something, but then they end up being the exact same line. So in that situation, there are an infinite number of solutions in common. But it's not, what we have to be careful about here, we don't want to say it's all real numbers or something, because it's not all the points over here and all the points over here, right? It is an infinite situation, but it's infinite in the sense that it's all the points that are falling on what ended up being the path of this line. Okay, so infinite number of solutions when they end up being the same line. All right, so we are going to associate that then with dependent lines. So the lines are no longer different, they are the same. So the lines are the same. So what I often say is think about a couple and they've been together so long. Sometimes people say, oh, they're so dependent on each other. It's like they've become the same person, right? Have you ever heard people say that? So, they've been together so long, it's like they've morphed into the same person. They're just so sometimes people even say they're so codependent. They're just so dependent on each other. They're like the same person. That's what I want you to think about here when they've become the same line. All right, but back to the inconsistent or consistent, we're still consistent here because we definitely have at least one solution. So we're definitely consistent. We definitely have at least one solution. Happens to be an infinite number. So at any time throughout this whole chapter, you may be asked to incorporate some of the vocabulary, which I'm going to try to do on some of the examples that we do here. So let's solve the system with our graphical techniques here, and then we'll also write out the associated vocabulary. So that's something where, if you're just asked to solve the system, you don't need to highlight the vocab every time, but there will be times you'll be asked for the vocab. All right, so I'll be honest, I think that in this section, slope-intercept y equals mx plus b is a really good choice for graphing your lines because we are wanting to be able to extend our slope. And by being able to extend our slope, that's what a lot of times is going to allow us to kind of get to the point where these two lines cross. So I would say slope-intercept is probably what you want to do here. So let's start on the first equation, which is 3x minus y equals 3. Let's start by subtracting the 3x. So negative y equals negative 3x plus 3. And then, of course, if I divide both sides here by my negative 1, remember to divide each term in your numerator by that denominator of negative 1. So y will equal positive 3x and then minus 3. Okay, in the second equation to solve for y, this one's a little bit shorter. All I have to do is subtract the 7 from both sides. So on this second equation, actually I'll come down below so it's not so crowded, I would have x minus 7 equals y, or probably we tend to like to see it as y equals x minus 7. All right, so let's go ahead and graph these lines and see if we can find that point of intersection. All right, so let's say we have our first line here. So let's take the y equals 3x minus 3. And so we start by going down 3. Our slope is 3 over 1. So remember that is where we go up 3 and to the right 1. So up 3 and right 1. Okay, so again, maybe we continue going up 3 and right 1. I don't know exactly how much I'm going to need. So let's say I only did, ooh, that wasn't so hot. Let's say I only did those points right now to start. And then we'll kind of come back and see what we need. All right, let's look at the, let's look at the second equation here. Let's look at y equals x minus 7. And so let's take a look at that one here. So y equals x minus 7. Sorry about my dog. All right, so we're going to start by going down 7, and then from there, remember our slope is a 1 over 1 here, so we are going up 1 and to the right 1. So up 1 over 1 is kind of my favorite, so this one's going to be pretty easy to graph. Okay, but here's what I want you to notice. If I keep extending to the right, guess what? Those lines, they were moving further apart here. So my lines are moving further apart as I extend to the right. So I need to extend down to the left. So on the first line, notice it's up 3 over 1, or going in reverse, down 3, left 1, down 3, left 1. So from that y-intercept, let's go down 1, 2, 3, and to the left 1. So that puts me at negative 1, negative 6. Let's do it again. Down 1, 2, 3, left 1. So I'm at negative 2, negative 9. Okay, so let's extend that line. And then on the second line here, let's do the same thing. So let's go, this one's easier, of course. We're just going down 1, left 1, and then if you notice, we just hit that point of intersection right there. So I'll be honest, what's going to happen on your computer is the computer will be perfect, and probably if you get 2 points done properly, you'll get it. So when we're graphing by hand, though, which you need to also be able to do, you need to be able to extend this slope appropriately here. All right, so our answer is simply going to be -2, -9. And again, the check is always helpful just to make sure that I haven't made any mistakes here. I would go back to the original equation, because if I made a mistake even in my first steps of solving for y, then I wouldn't get sometimes that error if I didn't plug back into the originals. So sub it into the first equation, it satisfies. Plug it into the second equation, it was the x equals the y plus the 7, and again, it works. So it's just kind of good peace of mind to do that. All right, now in terms of the vocab, so if I ask you to identify these inconsistent, consistent, independent, dependent, you should be able to look and say, okay, these equations are different from one another, from each other. So they're independent equations. And there was at least one solution. So we say that the system is consistent. So if you're asked for the vocabulary, then in this case, this is an independent and consistent system. If I don't ask you for the vocabulary, you just answer -2, -9. That is your answer. So we'll come back, we'll do a couple more next time, but that gives us our vocabulary and another example.